Equipment grounding conductors, often referred to as EGC, play a crucial role in electrical safety. Their primary function is to provide a low impedance path for fault current back to the source, which facilitates the operation of overcurrent protective devices like circuit breakers or fuses. This rapid clearing of the fault minimizes the duration of potentially dangerous voltages on conductive surfaces, thereby reducing the risk of electrical shock. The National Electrical Code, or NEC, provides detailed guidelines on the proper sizing and installation of equipment grounding conductors to ensure effective fault clearing and overall electrical system safety. Section 250.122 specifically addresses the sizing of equipment grounding conductors. This section stipulates that the size of the equipment grounding conductor must be determined based on the rating of the overcurrent protective device protecting the circuit. In simpler terms, the size of the wire used for grounding purposes is directly related to the size of the circuit breaker or fuse that's designed to protect the circuit. For 15 amps, 20 amps, and 30 amp circuits, which are commonly found in residential and commercial settings, Section 250.122 provides specific requirements. For instance, a 15 amp circuit typically requires a 14 American wire gauge, or AUG, copper equipment grounding conductor. A 20 amp circuit generally necessitates a 12 AWG copper equipment grounding conductor, and a 30 amp circuit usually calls for a 10 AWG copper equipment grounding conductor. These are minimum sizes, and larger conductors may be required in certain situations to meet other requirements such as voltage drop or to accommodate parallel conductors. Now let's delve deeper into the rationale behind these requirements and the implications of not adhering to them. The primary reason for sizing the equipment grounding conductor appropriately is to ensure that it can safely carry the fault current that may occur during a ground fault condition. A ground fault happens when an ungrounded conductor, which is typically the hot or live wire, comes into contact with a grounded surface, such as the metal enclosure of an appliance or piece of equipment. When this happens, a large amount of current flows through the equipment grounding conductor back to the source. If the equipment grounding conductor is too small, it may not be able to handle the fault current. This can lead to several problems. Firstly, the conductor may overheat, potentially causing damage to the insulation and even a fire. Secondly, the increased resistance of an undersized conductor will limit the amount of fault current that flows. This can prevent the overcurrent protective device from tripping quickly enough, prolonging the duration of the fault and increasing the risk of electrical shock. Thirdly, an undersized equipment grounding conductor may not provide a low enough impedance path for the fault current. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. A high impedance path will reduce the amount of fault current, which again can delay the tripping of the overcurrent protective device. In addition to ensuring adequate fault current carrying capacity, proper sizing of the equipment grounding conductor also helps to minimize voltage drop. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. By using a larger equipment grounding conductor, you can reduce the voltage drop and improve the performance of the electrical system. It's important to note that the NEC allows for the use of aluminum equipment grounding conductors in certain situations. However, when using aluminum, the conductor must be sized larger than a copper conductor to provide equivalent performance. This is because aluminum has a higher resistance than copper. The specific sizing requirements for aluminum equipment grounding conductors are also found in Section 250.122 of the NEC. Another important consideration is the type of equipment grounding conductor being used. The NEC recognizes several types of equipment grounding conductors, including wire-type conductors, metal raceways, and equipment frames. When using a wire-type conductor, it must be installed in accordance with the requirements of the NEC, including being properly supported and protected from physical damage. When using a metal raceway as an equipment grounding conductor, it must be electrically continuous and securely connected to all metal enclosures and equipment. The equipment frame itself can be used as an equipment grounding conductor if it meets certain requirements, such as being of sufficient size and having a low impedance path to ground. In addition to the requirements of Section 250.122a, there may be other NEC requirements that affect the sizing of equipment grounding conductors. For example, if the circuit conductors are upsized to compensate for voltage drop, the equipment grounding conductor must also be upsized proportionally. This is to ensure that the equipment grounding conductor can still safely carry the fault current. Furthermore, if the circuit conductors are run in parallel, the equipment grounding conductor must also be run in parallel and sized accordingly. The NEC also contains specific requirements for equipment grounding conductors that serve sensitive electronic equipment. These requirements are designed to minimize electrical noise and interference, which can disrupt the operation of the equipment. In these cases, it may be necessary to use a larger equipment grounding conductor or to install a separate isolated ground conductor. When installing equipment grounding conductors, it's important to pay attention to the quality of the connections. Loose or corroded connections can increase the resistance of the grounding path, which can reduce its effectiveness. All connections should be made using approved connectors and should be properly tightened. It's also a good practice to periodically inspect the connections to ensure that they are still in good condition. To summarize, firstly, equipment grounding conductors are essential for electrical safety, providing a low impedance path for fault current. Secondly, Section 250.122 of the NEC specifies the minimum size requirements for equipment grounding conductors based on the rating of the overcurrent protective device. Thirdly, for 15 amps, 20 amps, and 30 amp circuits, the typical minimum sizes for copper equipment grounding conductors are 14 American wire gauge, 12 American wire gauge, and 10 American wire gauge, respectively. Fourthly, undersized equipment grounding conductors can lead to overheating, delayed tripping of overcurrent protective devices, and increased risk of electrical shock. Fifthly, aluminum equipment grounding conductors must be sized larger than copper conductors to provide equivalent performance. Sixthly, the NEC recognizes various types of equipment grounding conductors, including wire-type conductors, metal raceways, and equipment frames. Seventhly, proper installation and maintenance of equipment grounding conductors are crucial for ensuring their effectiveness. Eighthly, other NEC requirements, such as those related to voltage drop and parallel conductors, can also affect the sizing of equipment grounding conductors. Ninthly, special requirements may apply to equipment grounding conductors that serve sensitive electronic equipment. And tenthly, always consult the latest edition of the NEC and local codes for specific requirements in the installation. Ignoring this code can lead to serious consequences for people, electronics, and structures. In addition to the specific requirements outlined in Section 250.122a, it's crucial to understand the general principles of grounding and bonding to ensure a safe and effective electrical system. Grounding refers to connecting the electrical system to the earth, typically through a grounding electrode system. This provides a reference point for voltage and helps to stabilize the system. Bonding, on the other hand, refers to connecting together all metal parts of the electrical system, such as enclosures, raceways, and equipment frames. This creates a low impedance path for fault current, ensuring that all metal parts are at the same potential. The combination of grounding and bonding helps to minimize the risk of electrical shock and fire. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. The grounding electrode must be properly sized and installed in accordance with the requirements of the NEC. The grounding electrode conductor connects the grounding electrode to the electrical system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The main bonding jumper connects the grounded conductor, typically the neutral, to the equipment grounding system at the service entrance. This creates a bond between the grounded conductor and all metal parts of the electrical system. The equipment grounding conductor connects the equipment grounding system to the equipment. This ensures that all metal parts of the equipment are grounded. In addition to the main bonding jumper, there may be other bonding jumpers required in the electrical system. For example, a bonding jumper may be required to bond together separate metal raceways or enclosures. When working on electrical systems, it's essential to follow safe work practices. Always to energize the circuit before working on it. Use appropriate personal protective equipment, such as rubber gloves and safety glasses. And never work alone. It's also a good idea to have a qualified electrician inspect your work to ensure that it meets all applicable codes and standards. Electrical work can be dangerous, so it's important to take the necessary precautions to protect yourself and others. By understanding the requirements of the NEC and following safe work practices, you can help to ensure a safe and reliable electrical system.